Alright guys, this is winter 2018 of the 0654 series, and we're looking at paper 6.1, that's alternative to practical. As usual in the paper, 6 questions. I'm picking out the physics ones, and I actually admit that when I first looked at this, I couldn't find the second physics one. It turns out it's this one, which is kind of weird one. It looks on this surface to me as a little bit like a chemistry one. We're thinking about the ideas of solutions and things like that, but actually it's a physics question, primarily a physics question anyway. We have got a student using a thermometer, okay, to measure the temperature T of a solution to the nearest 0.5 degrees. He records this in the table as we've got here. Okay, and then we've got all this stuff here. I think this is possibly why I thought it was a chemistry question, because we're looking at reactions, etc. But really we're talking about the measurements related. Okay, so it says here, first question that we have to deal with, thermometer readers are taken to the nearest 0.5 degrees. You can see he's gone for 20.5, 56.0, and then 0.5 down here, another 0.5 here. He's measuring to 0.5s. And then says, state the value of one division on the thermometer that makes this possible. And I think this is a terrible question. Don't think this is very well phrased. Okay, to be honest, I disagree with a lot of the physics here. However, we have to play by Cambridge's rules. Okay, to try and demonstrate this, I'm going to show you this thing here. Now, obviously, this is not a thermometer. This is a ruler. Okay, now what you should be noticing, is that when I look at these divisions, okay, the value of each of those divisions is 1 millimeter. Okay, and on our thermometer, the value of one division is 1 degrees Celsius. Now, why are we interested in this? Well, let's take the example of the ruler again. If I had a measurement which fell directly on, say, 13 centimeters, or directly on 13.1 centimeters, I can say very confidently that they are 13.0 or 13.1. However, if I had a measurement which went right in between, okay, so let me just write those down. We've got 13.0 and then 13.1. Now, obviously, if I had something directly between the two, then I could say, well, okay, then the value is 13.05. Now, I'm warning you, this is something that not everybody thinks, okay, not everybody agrees with this way of thinking. But to be honest, I don't. If I had a reading in between these two, I would choose one of them. I'd choose the closest one. However, some people, and CIE is one of them, allow you to say, well, if I've got a division, which is, say, 49, and I've got a division which is 50, and the temperature is somewhere in the middle, well, that allows me to take a halfway point, which would be 49.5. Okay, so even though my divisions are 1 degree Celsius, I have something in between that. I could call it 49.5. Okay, so just be aware that's what the question is going for. As I say, different exam boards, different people have different opinions. Certainly, that happens in science. Okay, don't worry too much. We're just considering the basic ideas here. Okay, so we're asked to use our data on our table to calculate the temperature rise. Okay, the maximum temperature rise. Now, what you could have done is gone through this paper and had a look. All right. The maximum temperature rise of the temperature during this reaction is, to be honest, it's the only temperature rise. Everything else is a temperature decrease, is a rise from 25 to 56. Okay, so we started with 20.5 to 56. 56 minus 20.5 is our 35.5. It gives us 35.5 degrees Celsius. Now, why we can only consider this as an estimate? Okay. Basically, why is this number perhaps not to be believed? Well, let's look at our data again. Okay, we're timing this thing a kind of weird scale. We're using 0.5 minute intervals, so basically 30 seconds between each interval. Now, for me, that is an interval which is a bit too long in some respects. And the reason being that it could easily change during that time. Okay, what could have happened during this time, is we could have had the temperature, for example, between here and here. That temperature could have gone even higher. All right, it might have peaked at 60 and then gone down to 56 by the time we measured again. Yep. Similarly, it might have peaked at 58 before we got, after we got to this 0.5. So really, we're not taking the data frequently enough here. All right. So the time scale used is quite long, 0.5 minutes, quite a long time, 30 seconds. You can imagine waiting, and it would be a long time, yeah, between the measurements. And so the temperature could have changed during this time. We don't know the temperature very well. How do we account for that? Well, do it more often, yeah. Take more data, and a really good one that people love in CIE, okay, is plot a graph. Don't just take the data, don't just record mounds and mounds of data. Draw a graph, see if there's any pattern in there. Maybe you can extrapolate your data out to see where you're at. Okay, next bit, really a calculations question. Okay, you're told that the energy is the volume of the solution J, right? Now, you may be wondering what the hell that is. We actually buried this information right in here. Okay, so this information, it's a bit dense, and there's a lot in there. However, you are expected to use it. Okay, so if you're given a number, be careful, that's the thing we needed there. That's 25 centimeters cubed. I can pick up my paper. Okay, 25, we've got 4.2, that number, don't worry about it. And then we've got 35.5, that was our temperature change. We multiplied it. I've got a number of 5 significant figures here. The question does ask you for 2 significant figures. Remember, we've talked often about, if in doubt, give 3. Well, here you are asked for 2, so give 2. Write down the full answer, then write down the answer to 2 significant figures. It will make your life a lot easier. Okay, so 3727, 3,700 joules. The last one, okay, your value of E is less than the actual amount of thermal energy, i.e., what we're really saying here, if I just add a bit, i.e., energy is wasted. Right? And this is a really common thing in physics questions about heating, okay, is the idea that energy will be wasted at some point. Now, in this case, obviously, we have got a plastic cup, okay, and these things will lose energy to the surroundings, okay, and that's why our energy value is a bit wrong. How do we stop that? Well, what we could do is we put a layer of insulation. Okay, you could suggest what that insulation could be. Cotton wool is a good one. Okay, or we could put a lid on there. Okay, and then what that does, well, the layer stops heat loss due to conduction, and the lid stops heat loss due to convection. I could imagine talking about another one, which would be heat loss to radiation. You could wrap this thing in tinfoil, because the heat, as it tries to come out of the cup, would be reflected back by the tinfoil and therefore kept into the cup.